everyone, this is lecture number 35. In this lecture, we are going to talk about validation of discrete time large signal model using MATLAB, and there will be two parts. So, this is part 1. So, in this lecture, first we want to recall our digital control architecture and MATLAB models. Then we want to show steps for simulation using MATLAB detailed switch models as well as discrete time large signal model, and then we will show MATLAB codes as well as the step by step method for model validation, and finally we want to show some validation case study using a buck converter. So, here I want to show the overall plan for MATLAB based validation. So, first step, that means we have a plug and play power stage MATLAB model of switch mode power converter model, and I just want to show, if you go to our MATLAB model. So, this is the MATLAB model and this is the power stage model, and I am talking about this model where we have plug and play MATLAB model. So, this is the power stage model. Then we will be talking about the digital controller, and then I will come back to the simulation again. So, the plug and play power stage model. Then next we also have code and Simulink customizable simulation environment, where we want to run the Simulink model from the .m file itself, and there we want to plug in all the parameters of the buck DC-DC converter. I will say all these steps will be discussed in detail. The third one, we also want to implement digital control, where we can also keep some real time reconfiguration possibility, but we want to implement digital control in Simulink. And finally, we want to validate our MATLAB model, that means our MATLAB switch model as well as the discrete time large signal model we want to validate. That means we want to validate the accuracy of the discrete time large signal model using MATLAB switch simulation. So, we will start with digital voltage mode control, and this we have discussed multiple times in the previous week. That means I think week 3 we have discussed various architectures and their MATLAB models. Okay, and week 2 we have discussed detail about the architecture. So, here if you see that we have an A to D converter, then controller, digital controller. So, and we know that there will be a delay because we are talking about a sampling clock, and generally the sample comes fast and we need to provide some delay, and this is the delay, and this delay we say Ts. This delay is used to accommodate the ADC conversion time and the controller computation time, and we will discuss that how to insert such delay in the MATLAB model, so that we can sample fast and then we will switch, because after taking the sample, then the controller voltage, which is the output of this controller, this will be ready after certain amount of delay, and when it is ready, then we will start the PWM switching operation, and that is driven by a trailing edge modulator. So, here we want to show the MATLAB overall plan. So, this is a device under test. That means I will show you the MATLAB Simulink model of the power converter. This is a power stage model, and from the power stage model we are talking about a voltage mode control. So, we are sensing the output voltage. Here also we can provide I would say a step down ratio also, but here we are directly sensing, and you can see outside we can also put an external current sink load. That means if you want to make a load transient, and we will be talking about a load transient case study. Then once you take the output voltage you sense, then this represent our ADC block, and we have discussed that this block consists of a clock triggered sample, zero order hold, sample and hold, or I would say block, zero order hold block, which is nothing but zero order hold block. Okay, so sample and hold block. Then after you get the sample voltage, and this clock will be using the sampling clock which we have discussed. So, we will first sample, then we will get the output voltage sample here. This is going to the reference voltage, then we are getting an error voltage. Error voltage is going through a controller, and since in the MATLAB, in the ideal environment, we are not putting any delay till this point, then we are inserting an additional delay here. So, this is my delay block, these are all delay block, this is also delay. So, here what we are doing, we are delaying the control voltage because that should be updated. Similarly, the sawtooth is also delayed and the switching clock is also delayed. So, that means we are synchronizing the switching clock with the sampling clock, and the switching clock is delayed by some Ts amount of time, and since the switching is starting after Ts duration, the RAM should also start with respect to the switching clock, and also the controller should be ready, the output of the controller should be ready at that time. So, all delay must be consistent, they must be same. Now, what are the steps for validation of discrete time large signal model? First, we have to run the switch simulation, actual switch simulation, where we need to provide initial condition for capacitor voltage and the inductor current, and then so let us will map one by one, that means let us go to this step. So, here I am showing the code where you can see that we are first calling the buck converter parameter file, that means we are loading the parameter file, then we are calling the DCM enable 0, that means we are operating at a synchronous mode, and we are also initializing, that we are going to discuss. This is the initialization of the inductor current as well as this is the initialization of the capacitor voltage, and we have discussed about the power stage, how to, where is the initialization block, because if you go inside, if you go to the current dynamics, so you will find this initialization will be here, sitting here. Okay. Then if you go to the voltage dynamics, that means the capacitor dynamics, then you will get the initialization block here. So, this initialization voltage we are actually setting from the .m file, and that we are discussing. Next step, that means we have initialized and then we will provide this. Next, we will initially run for one load condition, and if you go to that load block, that means I will be going this is load block, this is a load block. Inside you can see there are two load resistance R1 and R2. So, R is a continuous load resistance, but that we are not using for the time being. So, that means what we will do, initially we will run R1 resistance, because see this is the output voltage and this is the load current. So, output voltage by load current is nothing but, that means the load resistance, that means your load current is nothing but V0 by R1, and in the second case it will be V0 by R2. And if you go to the clock, I will discuss in detail, there is a clock which will take either 1 or 0, and it has a fixed frequency clock with time period T tran, and I will discuss what is T tran, and it will have a 50% duty ratio, and there is no phase delay here, and that means after 50% time of the T tran, first 50% time it will run R1 resistance, and then another 50% it will connect R2 resistance. Okay. So, that means we have a resistance and we are making a load transient. So, that we want to check, we want to show the validation for both steady state as well as the transient case, because we are talking about large signal model. Then we will apply a load step. I have told you that it will change to another load resistance. So, that will implicate a load resistance. Then we want to capture the time domain data and we will store, and I will show you all the step. Then once you store the switch simulation data, which include initially one load resistance, then after some time another load resistance with transient as well as the two steady state condition, we will store this data in the workspace. Then we will use discrete time large signal model, and we will provide initial condition for Vc and IL same as though in switch simulation. So, the initial condition must match, that means the large signal model should take the same initial condition of the switch simulation. Then we will run the discrete time large signal model for the first 1 millisecond, and you can also change this, it is not necessary it has to be 1 millisecond, you can take a shorter duration or longer duration, but initially we should take R1 resistance, that is for the first time. Then when there is a load transient, you change to R2 resistance and will run for some more time. Then we will capture all the variables. Then what we will do, now you change the load resistance to emulate a load step that we have discussed. So, R1 was connected earlier, now it will be R2 resistance, load resistance, and virtually it looks like a load step. Then again we will capture all the variable like a voltage and current data, and during the simulation runtime, and then we compare the captured discrete time model and we will compare with the actual switch simulation. That means, the last step will be, we will compare discrete time large signal model as well as the switch simulation result. So, let us go and check. So, this is the code that we are going to demonstrate in MATLAB. So, the first code, we are writing a digital voltage mode control in a buck converter, and that is a .m file. So, we will first clear the screen, then we will load the buck parameter, and again all these files are here. So, the buck parameter we are considering these are the inductor capacitor values, and we are initially talking about a reference voltage of 1 volt. Input voltage you can change in the code itself, you can use 12 volt or something else. Then we are putting DCM enable 0, that means it is in the synchronous mode, that means the current can go in the negative direction. Then initially N tran is the number of cycle. So, first 500 cycle it will run N1 R1 resistance, that means if I talk like this. So, I would say this duration is the N tran into T, where here it is the number of cycle and this time your R1 resistance was connected and this time your R2 resistance is connected and you are taking 50%. So, this duration is also N tran into T. So, that means the total duration from here to here will be twice N tran into 2 into T. Then we will start the simulation and then we will run for the total T tran time, which is the sum of this is my T tran time. Okay, we run this case. Now, we are setting some controller value, but again we have not yet discussed the controller design. So, we want to first show for a given set of controller how can we validate the model. Initially we are considering load resistance R1 to be 1 ohm. Since Vref is 1 volt, so 1 volt by 1 ohm is the 1 ampere load step for the initial case. Then we are changing the load resistance from R1 to R2, and R2 is 0.05 ohm. That means if you divide, that means R2 is we are taking 0.05 ohm. So, then what will be the load I02? It will be Vref, or I will say V0 by R2, and if the voltage is regulated at 1 volt, it will reflect, it will actually represent like a 20 ampere load change. Okay, we can also use a load step like a constant current load also you can use. So, here we are just objective is to validate, and we are again setting the initial condition. Now, there are two more initial condition. One is the sample voltage initial condition and is the integral initial condition. So, let us go to the MATLAB block and I will show you. If you go to the MATLAB block, here we have a digital controller, and if you go inside, this is the block, because we are talking about this is a PI controller, sorry, integral part of the discrete time integral control. This is the proportional control and this is the discrete time derivative control. Okay. So, if you go inside this block, you will find something like V integral, because you see this part is un plus un, this is the un, that is the output of the integral control, ui of n, that is the integral with nth interval, that value is equal to its previous value, that means ui n minus 1 plus ki into error voltage. Okay, that means we will discuss this. This is the discrete time integral gain, and then this is our discrete time derivative gain, which what is that? That will be kd into VEN, which is that the running sample error voltage minus its previous value. And if you go inside, we can also initialize, but here we are setting simply 0. The another part I want to say, if you go to the ADC block, that means this block, inside this block if you go, you can see there is a 0 order hold, but it will only enable whenever the enable, it should be enabled, and it will capture the signal at the rising edge of the trigger signal. Okay, and if you go inside output of the 0 order hold, this like a register, and here we are initializing VS initialization. Okay, so we have explained all the model part here, and let us go to the presentation. So here next we have discussed that this is our overall I would say the Simulink block, and we are running the Simulink file from the .m file here. That means if you look at the .m file, so this is the .m file, we are running through the simulation file. Then once you run, this will actually all the result, time domain result will be stored in the workspace. And you say there are many channel 1, channel 2, channel 3, channel 4, channel 5 and channel 6. There are 6 channels are there, and for each channel the time is common. So, this is like channel 1, channel 2 like that. So, time will be 0, then there can be first step delta T1, the second can be delta T1 plus delta T2, because if you are using a variable time solver, each step can vary. So, like that way it will go. Then channel 1, if you take this to be inductor current for example, so it will show the values of the inductor current at that time instant. Similarly, if you take, let us say here we are taking capacitor voltage, so it will be VCT. So, all these value, so that means in this vector you will get first is the time vector, that is why it is written, that means that T equal to Buck result, which is that the file name, that is the name of the workspace that where you are storing, it is a structure, it is a structure in time. So, you will get a structure. In this structure, if you first access dot time, so it will take the time vector, so time vector. Then you have a structure which will be dot data, and this data depends what is the size. So, if there are like it run for totally 20,000 let us say data point, that means the vector, that means I am telling the length of time, let us the time length is 20,001. Then since there are 6 channel, what is the data vector length? X. So, x here in this case which is here, it will be dimension will be first, that means 20,000 into 6 channel. So, you have to take one channel and then you will get the whole data of current whatever you are coming. Okay, so, like that way you will get, and then once you take all the separately, if you call that output voltage, capacitor voltage, sample voltage, inductor current. So, inductor current is the first channel. So, it will take the first channel and take all the data here, like that it can capture, then we will have a plot comment. Now, the next step, this is the simulation result I just showing. So, this is coming from a switch simulation, and the same thing we are talking about the sample voltage here, sample voltage, output voltage samples, because this is a sample voltage. So, you can see there is a slight delay and I will be showing the case study. Then we have to match the discrete time large signal model. So, what are the steps? In the discrete time large signal model, we will not close or clear the file. We may simply clear the I would say just the window comment prompt, but we should not clear anything on the workspace. Then we will call the Buck parameter. This part you can in fact disable, because this part will be common, it is taking from the switch simulation. Okay. And then next step I will go, it will take a discrete time model matrices, because any discrete time model you need on state A matrix, off state. For buck converter synchronous buck, if you assume that RDS1 for both high side and low side is same, so we are taking these two are equal. And what is this? This we have discussed that it is minus RE plus alpha RC divided by L minus alpha L alpha C minus alpha by RC, and this is exactly what is the Rn, and R of equal to Rn for this case. And B matrix, when the switch is on, it is 1 by L and 0, and when switch is off it is 0. And then Cm is the output matrix, which is the output matrix, it is alpha RC and alpha. Okay. Next, it is continuing. So, we are also giving the initial step, it is taking from the previous value, because we have defined this in our switch simulation. So, it has to take the same initial condition, then it will create a vector, then the sample voltage is nothing but the output matrix into xn state vector, and xn state vector initially loading with the initial condition. So, it is a sample voltage. So, the sample voltage can also like a V cap, another sample, it is the initialization of the sample voltage. This is the output sample instantaneous value, and this is the initialization which it can take V cap dot n, and then we are setting the integral, that we are setting 0 there. So, again the error voltage can also be defined, and so on scaling. So, I am not going to explain each and every step, but now we are plotting time versus the first vector, which is the inductor current, and the sample is that which is the output voltage. So, here So, here we can take, and then what will happen? Once the matrix are defined and that based on the load resistance, then it will run the loop, which is a buck discrete time dynamics. So, this is the model and the detailed code is there. It will enter into a loop and it will run from, that means totally n turn number of cycle it has to execute. So, it will start from 0 to n turn minus 1. Okay. So, that is what exactly. Then it will compute all these value control parameters, everything it will compute. From there it will compute the duty ratio, which is the V controlled by the VM. VM is the sawtooth that VM. Okay. So, this is the VM and this is the control voltage Vcon. Then we can compute the duty ratio, right? Because Vcon is to VM is our, the ratio if you take, it will be the duty ratio. Okay. Because we know that duty ratio expression is nothing but Vcon by VM here. Then we have to check whether the temporary duty ratio is it greater than or less than, because it is a running cycle. If it is less than 0, then we have to set the actual duty ratio 0. Duty ratio cannot be negative, and if it tend to become larger than 1, then you have to set it to 1. Its maximum value can be 1, and then the loop will continue, and then it will. This is the model. Actually, we want to show the ALR signal. That means we know that AXN plus 1 is that A equivalent into Xn plus B equivalent into Vn, right? What is A equivalent? For the buck converter, we know that A equivalent is equal to e to the power A on t, and this is exactly what. And for exponential case study, it will be written EXPM A on t in the MATLAB code. So, it will represent this in the MATLAB. Similarly, the B equivalent, if you see here, what is the B equivalent here? So, B equivalent will be a to the power A on t minus dt minus ts. This here inside you can see e to the power A on dt minus identity matrix into A inverse into B. So, this is the B equivalent matrix. So, this we are just plug in and then it is running, and this is the demonstration of the switch simulation. You can see, if you see, once it runs for 500 cycle, then we are changing the load resistance from R to R2. That means initially it was R1, now it is R2. Then it will again run for 500 cycle, and we are calling again the model matrix, because the model matrix has to be updated with the new load resistance. Then we are again taking the sample value, and then we are calling the buck function, dynamic function, which is again the same loop will run, but only with updated A matrix. Then the same thing we have discussed, and then it will validate the model. So, here we want to first show the MATLAB case study. Let us go to the MATLAB model. So, again we have discussed the overall MATLAB model. This is a load block that we have discussed. Now, we want to first show that this is our switch simulation. That means, first thing we are loading the buck parameter. This set the synchronous mode, synchronous configuration running for 500 cycle. Total run time, the simulation time is 2 times of 500 cycle into 2 into time period t. So, it is running for, so time period we are taken 2 microsecond. So, total number of cycle 500 into 2, so 1000. So, 1000 into 2 microsecond we are running for 2 millisecond. So, total simulation time is 2 millisecond. For this case, we have set some value Kp to be 20, you can set 10, whatever you want, no problem. So, you can set 10 also. Then we are setting a delay time of 10, that means the 10% of the time period, that means it is t by 10, and we want to see. And the ramp voltage magnitude peak value we have taken 10 volt, initial resistance 1 ohm, then the final resistance 0.05. And then we are initializing the inductor current and the capacitor voltage, and then we are initializing the sample value as same as the that is the capacitor voltage, initial voltage, and the integral term initial condition we are setting to 0. Then we are running the simulation through simulating that code, and then we are storing the data, and that we have discussed, and the plot command. And if you go to plot command, you will see the figure 1, we are plotting the inductor current, we are just leveling it. Then figure 2, it is plotting the output voltage as well as the sample voltage. So, this is sample voltage and we are leveling this. So, let us run the case study. This is the closed loop digital voltage mode control and we want to see what happened. So, here I have shown it is just switch simulation and I just want to show that from the very beginning that we are first running the simulation and the simulation start with sample. That means, we first sample and then we will go to, I would say the switching action. That means, if you go to the Simulink model, I want to show you that you can see here that since it is sample, so it is using this sampling clock, there is no delay. That means, the clock is the time period t, which is the time period switching period, and we are taking the uniform sampling. The sampling rate is same as the switching frequency. So, time period is t and there is no delay here. The next part, if you go inside, so up to this point there is no delay. That means, it is computing the error voltage as per the running sample. Then if you go inside, it is actually discrete time integral control and this is the discrete time derivative control, and we have already discussed this, and this is a discrete time proportional control. And then if you add up, then you will get a PID controller output, and this output is going. Now we are delaying. If you go inside, we are delaying by Ts amount of time, and I told you the same delay should be applicable for the RAM, and for the clock the delay is set here. So, you can see the delay here. So, that means, all the switching clock is a delayed version of the sampling clock, which is the time period is same, but the Ts amount of delay. RAM signal is also delayed, and then the output of the PID controller is also delayed. Now, we have shown the case study. So, in this case study, that is what it is reflected. So, if you initially sample, then it is coming. So, it is getting updated at every 2 microseconds. You see 0, 2, the samples are updated, but the switching is happening little later because we are switching. Then if you go to the transient case, you can see that this is where the load transient is happening. Okay. Next, we want to run the discrete time model. So, you go to the discrete time large signal model, and since we are using the same controller gain, so you just commented this line and let us run the case study. So, if you run it, then I want to show that, let us go to the output voltage plot first. So, output voltage plot, if you go, you see our discrete time models are derived between two subsequent samples. So, every time whenever we are sampling, it is exactly matching with the discrete time model and the sample values are matching perfectly. Okay? That means, they are matching perfectly, and you can see that it is taking the identical voltage. So, they are perfectly matching. Okay. Same thing is happening even during transient. You see, the during transient they are exactly matching. That means, the sample which is captured through switch simulation and the discrete time model at every sampling instant, they are identically matching. Okay, that means, the model is perfectly valid, and you can see there is a. So, if you go to the inductor current waveform, I want to show that if you take the inductor current again, if you run through this, you see it is matching from the very beginning. That means, it is matching like this every cycle, and the switching is actually happening after some delay. That means, we have discussed that if you consider interval 2 sampling with a Ts amount of delay, so it is delayed, and this delay amount we have set to 20 nanoseconds, 200 nanoseconds. So, you can see 0.2 millisecond means 200 nanosecond. Sorry, here we have taken, sorry, our time period is actually time period is 2 microsecond. So, that by 10, so 200. So, it is 0.2 microsecond. So, it is 0.2 microsecond, that means 200 nanosecond. Yes. So, it is that perfectly matching, the inductor current is matching perfectly. So, that means, what we can say that our investigation, that means, the matching is perfectly happening. So, in summary, we have recall, we have discussed the digital control architecture, particularly voltage mode control architecture and MATLAB model. We have discussed the step for simulation using MATLAB detailed switch model and discrete time large signal model. Then MATLAB codes and step by step method for model validations, those are discussed, and we have also considered some simulation case studies using a buck converter. That is it for today. Thank you very much.